morning, everyone. Welcome to, oh, I think I went too far. All right, welcome to your guide to tuning foundation models. Thank you for showing up at 8 a.m. My name is Nikita, and I'm joined by my teammate Jarek. And today we'll be talking a little bit about how to train foundation models on Vertex AI, and then Hossein from Flybits will take the stage to share with you some practical lessons about tuning large language models. But before we get into talking about different methods and ways of tuning, I just want to spend a minute talking about why we might want to tune a foundation model on a custom data set in the first place. So if you've had a chance to experiment with some of these foundation models, you might have noticed that one of the things that makes them so powerful is that a single model can be used for so many different tasks. So depending on the way you structure a prompt, you can use an LLM for something like brainstorming. If you write a different prompt, you can use that same model for classification, and that same model for extraction, and that same model for summarization, and you get the idea, right? Depending on how you write a prompt, we can use these models for all sorts of different tasks. But depending on the task you're trying to solve, coming up with prompts can be tricky. Small changes in wording or word order can impact the model results in ways that aren't entirely predictable. You can't really fit all that many examples into your prompt, and the more examples you try and shove into your prompt, the more it eats into your input context window. It's a very iterative process, and even when you do find a prompt that works well for your use case, you might notice that the results aren't entirely consistent. So what I'm saying is that if you spend enough time trying to experiment and prompting large language models, you kind of start to realize that a single model that can do absolutely everything has some practical limitations. But luckily, if we do task-specific tuning, we can make these models more reliable for certain use cases. So today we're going to introduce you to the two different tuning services on Vertex AI. We have supervised fine-tuning, which is well-suited for tasks where a human could kind of relatively easily come up with a standard or correct answer that could be kind of justified or explained. But there are some use cases where it's not so easy to come up with what the correct answer is. You can think of that as like a chat use case, where maybe if you were given a couple different examples of answers, you'd be able to pick which one was better, but it would be hard to say exactly what makes the correct answer correct. And for those types of scenarios, reinforcement learning from human feedback is really useful. So I said there were only two services, but actually, since you all showed up at 8 a.m. today, I'm going to let you in on a secret. We have distilling step-by-step and experimental. We won't be talking about it today very much, but this is a tuning technique where you transfer knowledge from a larger model to a smaller model. So stay tuned for that. Again, we'll be focusing on supervised fine-tuning and RLHF today. But just wanted to let you know we have this in experimental, and stay tuned for more information. Okay, so broadly speaking, when it comes to tuning models, we can kind of take two different approaches. So if you're already familiar with machine learning, if you're familiar with transfer learning, you might know about full fine-tuning. And this is where we take a model that's been pre-trained on some generic data set, we make a copy of that model, and then we retrain the model and we update all of its many weights. But with these foundation models, they're very, very large, probably larger than models that most of us have been used to working with in the past. And so a full fine-tuning job requires a very large training job. It's a lot of compute. And then at the end of that, you have this giant model that now you have to serve. So in a lot of cases, this isn't necessarily the best option. And so alternatively, what we can do is something called adapter tuning, where we're only updating a small subset of the model weights and not all of the model weights. So on Vertex AI, currently for both supervised fine-tuning and reinforcement learning from human feedback, we are releasing adapter tuning, which enables tuning the model to specific tasks without having to rebuild the entire foundation model. And this happens via parameter-efficient techniques. So these small subset of parameters might be a subset of the existing model parameters or an entirely new set of model parameters. My diagram here is a little bit simplified, but hopefully conceptually it gives you the idea of what's going on here. The exact set of parameters that are updated depends on the technique you're using, and the kind of optimal methodology is an open area of research. It keeps changing. But regardless of which kind of method you choose, there are some big benefits to adapter tuning. So the first is that you get faster training because there's fewer parameters to tune, and you also need less training data than you would compared to full fine-tuning. And then adapter tuning also makes serving models simpler as well, because you don't have to serve the entire base model. You just have to worry about the specific tuned weights you have and then attaching those onto your base model, and you're good to go. And the way that this works in Vertex AI is that adapter tuning jobs run on cloud TPUs or GPUs via the Vertex AI training service. Vertex AI creates a separate tenant project for each customer project, and the training workloads run on VMs in that tenant project. So the key takeaway here is that your training data, your input prompts, and your tuned weights never leave your environment, and they are never used to tune the foundation models. So we have a whole white paper about this. If you want to learn more and learn more about how that works, I encourage you to check that out. I've got a screenshot here. It's called Adaptation of Large Foundation Models. Okay, so full fine-tuning and adapter tuning aside, let's talk about the practical things. How do you actually use these services on Vertex AI? And we're going to start with supervised fine-tuning. So like I mentioned before, this is well-suited to tasks where a human can kind of come up with a standard or correct answer that can be justified or explained relatively easily. So you can think of good use cases as, you want to teach the model like specific structures or formats for generating outputs, specific behaviors like when to respond with a terse output or maybe being more verbose. And the way you structure your data is in each input row or record in your data set is your input prompt followed by the expected output from the model. So one way I like to think about these use cases is supervised fine-tuning is well suited for examples where you want to take data in one format and convert it into another format. And while that might sound very boring, there are a lot of different use cases that kind of fall under this pattern. So something might be taking a conversation and removing all the PII, or taking some unstructured description about a clothing item and then restructuring the key attributes as JSON, or taking a user request, extracting the key pieces of information, and then reformatting it in some domain-specific language. In all these use cases, there is some notion of what is the correct answer, and they make for very good use cases for supervised fine-tuning. And you can kick off a supervised fine-tuning job from the Cloud Console, or you can use the Vertex AI Python SDK if you like. But regardless of what methods you choose, all of the Vertex AI training services are built on top of our existing MLOps tooling. And so this means that all of your training workflows are orchestrated as Vertex AI pipelines like this one here. So you can always monitor them in the Cloud Console, and all of your tuned models will be available for you in the model registry. So with that, I'm going to hand it over to Jarek, who's going to talk more about the RLHF service on Vertex.
Okay. So as Nikita mentioned, there is a set of NLP tasks which can be very well addressed using techniques described before, so supervised fine-tuning, especially tasks where mapping between input and output is very well defined, and outputs are unambiguous. So tasks like classification, some forms of extraction, entity extraction, extractive Q&A, even some cases of summarization, like extractive summarization, when it's pretty well defined what's the right answer. But there's many other scenarios where it's difficult to say what's a good answer. Let's say a summarization. Text may be summarized in many different ways, and each of those ways may be correct, but may be preferred by different people, by different audiences. So there is this kind of loosely defined element of a preference, and a preference for maybe even a specific audience or a specific group of people. And the reason behind it is that when we pre-train the models and when we fine-tune the models using supervised fine-tuning, the training objectives, in a case of pre-training, predicting the next token, or in case of supervised tuning, mapping the input to the output, do not really reflect what we really want to do, which is to train the models which follow user instructions, user intentions, and do it in such a way that they are helpful, they are harmless, and they are honest. Those three words are not random. There's in fact a paper which explains exactly what we mean when models have those characteristics. And it's very difficult to capture those objectives using the standard objective functions used when we use pre-training or supervised fine-tuning scenarios. So there's a lot of techniques. This is in fact a very exploding field of trying to align the models better with user intentions, user preferences, or with some universal values, which we as humanity may value and respect. One of those techniques is RLHF, and in my talk I'm going very briefly describe RLHF algorithm as it was introduced by OpenAI and as we implement it in our solution, and then we'll go through how to use it in Vertex environment. So let's start with what is RLHF. So RLHF technique was described in pretty good detail, in fact very good detail. It's between the main part of the paper and appendices close to 70 pages. In this paper published by OpenAI, training language models to follow instructions with human feedback. In this paper, they refer to the technique described in another paper from 2017, Deep Reinforcement Learning from Human Preferences. This is a paper which was written jointly by DeepMind and OpenAI. And in this paper, they introduced technique of introducing human feedback into a standard reinforcement learning loop. In this case, they were training small robots and trying to build the models which play Atari games. But the bottom line is that the key innovation in those of the techniques was incorporation of the human feedback and human intentions into the training process. So let's quickly go over RLHF. RLHF usually comprises 3 stages. You start with a model you want to fine-tune. This model may be a base pre-trained model. It may be the model which was instruction-tuned. It may be a model which was even supervised tuned on a specific set of tasks. Yes? But you start with a model, and then you use this model to generate outputs. You have a set of prompts, and you use this model to generate the outputs. And for the single prompt, you generate multiple outputs. Like if you read the paper, OpenAI generated between 4 to 9 responses to a given prompt. And by changing some of the parameters, like nucleus sampling or those common parameters you can control when generating outputs to the prompt, you will get different answers. Another is a key step in the process. Those answers are now rated by humans. And the way they are rated, to avoid some issues, yes, with absolute scales, the human laborers will compare one answer to the other, and they will specify which they prefer. And this is your data set. Yes? So you create basically a data set, sometimes referred to as a preference data set, and you will see the exact format of this data set as we require that in our services. But conceptually, the data set has a prompt. It has 2 answers, possible answers to the prompt, and it has a label, which defines which of those answers was preferred by a human laborer. So this data set captures preferences of humans. Now, to be more precise, it doesn't capture preferences of all humans. It captures preferences of a specific labeler or laborers who were used to create this data set. Now, this data set is used to create something called a reward model. This is the model. It's effectively a regression model, which takes now an input sequence and returns a scalar value. And this value denotes how well the model preferred an input sentence. That's why it's called reward model. So the higher the number, the better the input sequence or response from the model is aligned with the values and intentions captured in the reward model. Now, as you can see on this diagram, RLHF and reward model, the way I defined, is only one way of incorporating human feedback into this fine-tuning loops. Yes, there are some other methods. There is something which is pretty hot these days in research called constitutional AI, and most vendors apply a few different techniques which go beyond the straightforward RLHF in their implementations. We do it too, yes? There's a little bit of a magic happening in those implementations I cannot talk about, yes? But it's a very, very active area of research, and there are constant improvements almost on a daily basis. Okay, so now we have a reward model. So this reward model is now used in the second stage of training, when we now fine-tune our original model, utilizing this reward signal from a reward model as part of an objective function. And the algorithm which was described by OpenAI and which we also use in our implementation is called PPO, Proximal Policy Optimization. So this is a pretty old, well-understood, very well-performing algorithm from reinforcement learning. And one of the key features of this algorithm is that in addition to incorporating reward signal into the fine-tuning process, it also makes sure that you don't overfit the model to the reward signal. So it kind of, there is a penalty component in the objective functions which makes sure that as you tune the model, it stays relatively close to the original model while incorporating the feedback and assessment of the responses to the prompts as defined by the reward model. And why I'm mentioning that is you will see when we go through our pipeline that there's a key parameter you have to configure, which controls this penalty, yes, and controls basically the PPO algorithm. Yeah, so that's the process. Again, you start with creating a preference data set. In reality, this is probably one of the most complex parts. Yes, how do I find labelers who can properly create this data set? And if you read the paper, it may be in fact a pretty complicated process, an expensive process to create this data set. Then we use this data set to train the reward model, and then we use the reward model in a reinforcement learning loop just to fine-tune our LLM. By the way, reward models also start as LLMs in this context. Yeah, they are usually a little bit smaller, or maybe a little bit smaller than an LLM we are fine-tuning. OpenAI mentions 6 billion parameters for the base for a reward model. Our reward models are about the same size, yes, when you look at implementation. But they can be as big as the model you tune. If you read through Anthropic papers or some of the papers from DeepMind, they used really large models as reward models, models with 70 billion parameters and so on. Yeah? So it is still a choice, yes, of your implementation and a little bit of experimentation which is going on in that space. Okay, so this is the algorithm. How did we, first of all, does it work? Yeah? No, it does work. Yes? This is a couple of charts. One chart, the chart on the right side on my right side of the picture, the diagram, is from original OpenAI paper, which shows you performance improvements you can get after RLHF tuning the model. The measure is win rate. Yeah? So basically, if somebody would assess now two answers to the same prompt, one generated by a base untuned model and one generated by the model tuned with RLHF, one answer wins. Yeah? So as you can see, the win rate for those RLHF tuned models increases dramatically over non-tuned models. And in fact, in the paper, they quote that the small RLHF tuned model 1.3 billion parameters perform better on this test than a full 175 billion GPT-3 model. So there is definitely improvement in some cases. Now, not everything is perfect because there are also some side effects of RLHF tunings. I don't have time to talk about it, but there's always a little bit of a win-lose situation when you perform those tunings. And the chart, the other chart are some of our experiments with different models. So as you can see, we see very similar, proportionately very similar improvements in the performance of the models for different types of models. There's different sizes of T5 models and our text bison model, which is kind of a flagship model in our API. Okay, so how is it implemented? Similarly to the supervised fine-tuning service, it is implemented as a vertex pipeline. You see the vertex pipeline on a chart. It's relatively complicated, so I'm going to drill down to specific parts of the pipeline in the following slides. But this is the pipeline, which implements the full RLHF workflow as I described a few minutes ago. And how do you access it? Again, yes, it's a pipeline, which, by the way, we open sourced. As of this week, you can look at this pipeline on Kubeflow Pipeline's GitHub repo. We have implementation of this pipeline. And we also included this pipeline in a Google Cloud Components SDK. So you can create the pipeline by importing RLHF pipeline from this package. And then following the standard process with Kubeflow pipelines, you compile the pipeline into the intermediate representations, which will be then processed by Vertex pipelines, and you submit a pipeline job. And the pipeline job will have a set of parameters. There is quite a few of them. I only listed a few examples. First of all, obviously, you specify location of your data sets. There are parameters which control how many steps you will execute for tuning, for creating, training the reward model, for tuning your base model, and there you go. The last parameter is this coefficient, KL coefficient. This is the coefficient which controls this penalty, which controls how far the tuned model will deviate from the base model. Yes? And the lower the value, the lower the penalty. If you set the value to 0, it will not force any kind of alignment with the base model. Okay, so let's drill down to a few aspects of this pipeline. These are the formats of a data set. For the preference data set, as I described, both data sets, by the way, are JSON-L files. The preference data set will have a field called input text. This is your prompt. It will have two possible outputs, so two possible generations from the model for this prompt, candidate 0, candidate 1, and it has a field choice which specifies user preference. In this case, the candidate 0 was preferred by the human laborer. The second data set, this is the data set which is used in our reinforcement learning loop to tune the model. Prompt data set is very simple. It's basically a set of prompts. Now, it is important that both prompts in the preference data sets and in your prompt data sets, they should come from the same distributions, but they should not be the same, because it's standard machine learning. Yes? You want to avoid target leaking and all those other effects, and you have to make sure that they are sampled from the same distribution, so you have a meaningful training workflow. Now, when you drill down to the pipeline, this is kind of the tuning, the training part of the pipeline. So the key steps is this reward model trainer. This is the step which encapsulates the code, which trains the reward model. And then the reinforcer step, this is the reinforcement learning step, which fine-tunes the base model. There is a bunch of helper components. This resolve machine spec component is kind of important. Similarly to supervised fine-tuning, we can tune the models using GPUs or using TPUs. And it kind of depends on a region in which you want to tune. So if you want to tune on GPUs, we will use 8 A100 GPUs, the model with 80 gigabytes of device memory. And if you tune on TPUs, we'll use 32 slice TPU v3. So the TPU slice, v3 TPU slice with 32 cores. This is the minimum requirement to run the pipeline. So after the model is tuned, the models are stored in Google Cloud Storage in your tenant projects, and then there is a subgraph which deploys the model to Vertex prediction. Yes, so this is the standard deployment process. We register the model in the Vertex model registry, and then we deploy the model to Vertex online prediction endpoint. And at the end, you will have a model deployed to Vertex prediction, and you can now use the tuned model exactly the same way you would use any other model in Vertex, and using exactly the same API you would use to access models like TextBison or other generative AI models which are exposed. No difference, nothing specific to that. And there is another part of the pipeline, batch inference. So what this step in the pipeline does, if you provided a test data set, we will run the batch inference of this test data set and generate responses. So you can later use some form of evaluation if you want to compare those responses to other models. We do have other pipelines, evaluation pipelines, which can help you with this task. If you want to do the win rate analysis, if you want to use, again, humans to validate your responses, or if you want to use some kind of automatic evaluations like an SNX pipeline, which is covered in some other talks, which uses an oracle model to make those decisions. Yeah? So the bottom line, it's a pretty comprehensive, very easy to use pipeline, which implements quite complex workflow and quite complex algorithms. And that's it for my part of the presentation. And now I will invite Hossein to the podium to talk about really interesting stuff. Yes, how it is all applied in practice.
About 9 years ago, I had a similar but disappointing experience as a graduate student. I hosted a workshop at 8 a.m. at an academic conference about contextual fine-tuning of models, and almost no one showed up. But look at you. It's great to have you here at 8 a.m., so maybe a big round of applause for you, the audience, for showing up at 8 a.m. My name is Hossein Rahnama. I'm founder and CEO of Flybits, headquartered in Toronto. I'm also a professor at MIT Media Lab in Cambridge, and representing the work of my team today that they are working on some unique capabilities allowing large language models to be used in very specific granular privacy-preserved settings when you don't want your data to leave your premises and you want to contain their integrity and privacy. So let me just go to this one. Language models are great. We can do so many cool things with them, from answering questions to translating to reasoning to code completion. And they are just getting better and better and better as we are having more parameters in these models. But we may agree that they lack a few things. It's sometimes difficult to apply them in a very specific domain. The more specific they become, you require more tuning capabilities. And also, they lack context, right? The big thing is, do you understand the intent of those prompts and questions? Why are you asking that question? Who are you asking that question as? Are you a student? Are you an engineer? What is your intent? So those are some of the things that our team members are working on to figure out if we can capture intent when you are creating these prompts. And also, they are not very good with multi-hop reasoning, like when you have sequences of logic that will need to come together and infer. Language models are not good with those. Few examples. Flybits does a lot of work in the financial space. For those of you familiar, banks have a lot of data distributed and siloed in multiple repositories. They have different semantics, different ontologies. So if you have a pre-trained language model and someone wants to understand the relationship of home financing versus the risk guidelines, just imagine the types of graphs and nodes you need to put together to really personalize that answer. And at the moment, yes, we can use very fine-tuned language models, but they are not very scalable, and they're very expensive to maintain and scale. Think about other examples, like two individuals, one a student, one a neurologist. Not that neurologists make a lot of money, but my team came up with this example, are more or less asking a question about a trip to Greece. But think about the context of that question. One may have budgetary confinements. The other one is actually looking for a plan. So although the prompt and the question is the same, there's a lot of context in that question that you need to address. And how do you really bring that embedded personalization into these prompts? So that's another thing that our team is working on. And most of you are familiar with this. Language models are very bad when it comes to multi-hop reasoning, right? The classic example in the literature, a farmer has a certain number of chickens and rabbits on this farm. The total number of heads is 20, and the total number of legs is 58. How many chickens and how many rabbits does the farmer have? You are super smart people. You can answer that question relatively quickly. Language models can't. The reason is, well, there are lots of unknowns. They need to formulate the context. They really need to figure out the equations, and then they need to explain the output. So explainability and audit also becomes an issue. And there's a lot of literature these days about how they are addressing these issues. So our team is working very closely with Google. These are, summaries of how we are using tuning. Most of you are familiar with this. Usually I can divide them into two key areas. One is in-context learning, in which the commonality in them is that you really keep your model frozen. You don't touch your language model. And then in some cases, you may provide some examples and you may get an array as an output. That's the first one. Sometimes if you need a vector as an output and embeddings, you can still keep your model frozen, get an embedding and use it for retraining or chaining it with other models. This is usually useful when, token sizes are important for you. You have, confined questions and answers, and that's usually how you use one of these techniques. And Google, as Jarek mentioned, they have some very good models with text bison and text embedding with that. The other approach is when you have a lot of data, and usually that data is labeled. Token size is no longer that much of an issue, so you actually make your model tunable. So it's not frozen anymore. It can become sentient, and it can change, and it can become dynamic. Doesn't mean anyone is better than the other one, but usually you can address some of the requirements in terms of which one to use based on which context. So one of the core examples I share with you, we do a lot of work in the financial space, a lot of credit card companies. So we have the ontology and the semantics of the credit card business. Our prompt engineers provide about 20 examples, more or less, for a particular workflow. We fine-tune the LLM, and then the expectation is that a new request will generate a new response in form of natural language, or even if you want, in form of a script. So this is an example. If you just let me tell you a little bit about what Flybits does. We are very good in generating contextual experiences for our customers. In the old days, we also had think about a visual journey builder, put the structure in place, put the entities in place, build the workflows. Now, a lot of that is getting replaced by language models. So instead of expecting a marketer or a designer to go and build this from scratch, they can just type, or they can just talk even using audio, and then the experience will be created for them. So in this case, the prompt is, someone says, I want to create an experience that can reduce fraud. I want to make sure that I target transactions more than a particular dollar value. And then you have elements mapped that understand the request type, request objective, request rule, and then the action. So just by about 20 examples, you will be able to generate a script, and then that script can be used for any type of workflow that you want. This is a classic example that we use some of these language models. So the pros and cons, they're relatively easy to use. They're becoming easier and easier. They have data efficiency, they have versatility, and they have fast training. But what are the negatives? Very, very prone to biases, right? You need to really find a balance between how generalized or how fine-tuned you want the model to be. If you generalize too much, you may have ambiguity. If you really fine-tune it, then you really may miss that generalization capability. So those are all the things that you can address in your prompt engineering exercises. The other thing that I would like to show you is a capability we created called Nestor. Anyone here familiar with the Tintin comics, the comic book? It was more popular in Europe. There was a character in that book called Nestor who was the concierge for Captain Haddock, and what he was very good at was that before the captain asked for something, he had it ready and he delivered it. So that's why we call this Nestor. And the premises of that are two things. One is to really use neurosymbolic approaches to reason using graphs. So the idea is the input comes in as natural language. We have a fine-tuned Palm model, And then using reasoners and using symbolic representations, we have the ability to go and consult a large data sets that are being formed in form of graphs. And then you can query the graph, return it as a symbolic representation or script, and then you can translate that into natural language again. So the example of that is a marketer, an experienced designer comes on an interface and say, I would like to build an experience that provides 15% bonus to my loyalty program providers in Canada, right? That's cool, you know, that I will benefit from that. So what then happens is that you will use your tune model, you will create a symbolic representation, you reason through querying your knowledge graphs. But the problem with this example, if you consult your location model, is that you have a lot of ambiguity that the tune model understands. So it comes back again with a prompt asking for more information. It asks the user, tell a little bit more about who do you need to address in Canada? People in Canada, outside Canada, people who travel, and just going through that elicitation and feedback, you will get responses that are more personalized and more relevant to what you want to do. The last thing I want to highlight, which is a big strategy for us, is, you know, prompt engineering is amazing. It's becoming more and more advanced. But wouldn't it be great if you can have recommendation on auto prompts? What are the good questions you can ask from your data? That's where we spend a lot of our time. You know, it's what is the right question to ask? And that also goes back to some good philosophy. So our researchers working on knowledge graphs to really combine semantic networks and semantic graphs with AI models graphs and combine it so that we can actually get reasonable or reason-ready graphs for querying. So the process, without going through the details, is you have these, think about a knowledge graph that represents, I don't know, some sort of an ontology, banks or healthcare, or even more granular like credit cards or loyalty. You use some sort of a pre-trained graph neural network to really understand it a little bit better and add to it if it can. Then you also have an AI model graph. An AI model graph, you know, your semantic graph could be just nodes and relationships. Your AI model graph can also have weights and relationship and function. So for example, you may have a model graph that has a Bayesian node for calculating risk, and it may have a causal inference node, and it may have a fuzzy logic node. And then it really understands in what situation, in which context, which node to use for that type of inference. When you bring these two together, kind of the semantic graph that you have and the AI graph, then you're going to have a reason-ready graph that is going to be very powerful when you query it. So first step is have an AI model graph. There are a number of them available. Your data scientists can build some. Then you use a pre-trained GNN against your ontologies and semantics. You basically combine them in some sort of a unified graph, and you make your graph reason-ready. So that's becoming, this is one of the approaches that we are using for generating auto prompts. That's a very interesting field for us. Like, tell me about your data, tell me about your graph, but also tell me what are the 10 best questions that I can ask from it. And if you wear a contextual lens on it as well, that becomes more interested. I am interested to ask questions about my data in a risk situation. I'm interested to ask questions about this data when I want to cross-sell and upsell to my customers in this location. So now you're getting to a model that, of course, you will need prompt engineers, but you can really accelerate your workflow when you're building such systems. So to summarize, I can really categorize it as, first and foremost, there is a human element here. It was great to hear from our colleagues that there are human-centered approaches for this. And I would say at least our experience is that even your fine-tuning teams, your ML teams are very interdisciplinary. If you just have a team that are all AI scientists, you really miss the context of the types of knowledge graphs that you got to create and the context. So go back to the old saying that build teams that you can feed them with a large pizza, and really, have complementary skill sets, especially for those questions and knowledge graphs to be created effectively. I think where things are going is that it will be a fascinating field to see how LLMs are becoming more personalized, like really understand intent and also understand who's asking and why they are asking. I think this ability of building reasoners to translate between objects and scripts and natural language and learn from that is also becoming a super interesting area. And yeah, just we all know LLMs are great. They continue to get better. There's one thing to keep adding parameters, but there's also another thing to build ecologies and ecosystems around your models so you can really contextualize and essentially build an inference router that you may have tons of models and it can know how to combine them. And if you have a user interface allowing you to do that effectively, I think that will be great. And the last thing I say is that we are all fascinated by AI, but I think your data strategy is also super important. I was impressed yesterday during the keynote to hear about, I think they were called extensions, that you can keep your data in your premises, not moving it into a centralized repository. I mean, we used to have TEAs, trusted execution environments and all that. I think these are advancements of that you can now have a privacy-preserved local environment to benefit from LLMs, but then the concerns of legal and data portability, data tokenization will become much, much easier to address. So if that strategy, which is data decentralization, explainability, auditability, portability, goes hand in hand with some of the things that I shared with you that our team are working on, I think you will really find scalable frameworks for AI strategies. I think that's all I had to share with you. And with that, I'll pass it back to Nikita. And yeah, happy to take QA. Thank you.